Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to our first lesson on problems of minimization and maximization. In our last lessons, we learned about the first and second derivative tests. In this lesson, we will begin to see the practical applications of differential calculus. We will look at questions that involve maximizing and minimizing area. This should be a fascinating lesson. Let us begin. A farmer wishes to build a fence to enclose a rectangular field that borders a river. This means that no fence is needed along the river, and he must only build 3 sides. He has 360 meters of building material. What are the dimensions of the field that has the largest area? Students, this seems like a very simple problem. Take a few minutes to try to solve it on your own.
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Welcome back, students. I wonder what answers you found. Let us work through this question, and we will compare answers at the end. There are many possibilities, are there not? For example, the field could be 120 meters to a side. It may have a short side of 80 meters and a long side of 200 meters. How can we know which of these possibilities yields the maximum area? Let us begin by stating the general case. We wish to maximize area A of the rectangular region. Let X and Y be the width and depth of the rectangle. If this is the case, we may express A as the product of X and Y. Since we want to express A as a function of one variable instead of two, let us eliminate X by expressing it in terms of Y. In order to do this, let us use the given information that the total length of the fence is 360 meters. X equals 360 minus 2y. A of y equals 360y minus 2y squared. So, we know that y is greater than or equal to 0 and less than or equal to 180. The function 360y minus 2y squared is continuous on the closed interval of 0, 180, and it is differentiable on the open interval of 0, 180. A prime of y equals 360 minus 4y. If we take a prime of y to equal 0, then y must equal 90. In this way, we have discovered that 90 is a critical number. To get the maximum area, we calculate the value of A at y equals 90, the critical number. The two end points of y are 0 and 180. A of 0 equals 0. A of 180 equals 0, and A of 90 equals 16,200. This is the maximum value of the function. Therefore, y equals 90 meters and x equals 180 meters are the dimensions that give the optimal answer to this problem. If you got the same answer, good work. It is fun to see how calculus can be applied to real problems. Let us try a different type of question. The equation 1500 multiplied by 1.75 minus x gives us the number of bus riders traveling from the suburbs to downtown each weekday. Using this equation, please find the value of x which will maximize total revenue. In this case, x represents the bus fare. Working with a partner, please try your best.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again. Let us see if you and your partner were able to find the correct solution to this problem. We know that a function will have a maximum or a minimum at the numbers where its derivative is either 0 or undefined. Therefore, we must find the derivative of our revenue equation. First, we find our revenue equation, which is equal to the fare times the number of riders. Our revenue equation becomes R of X is equal to 2,625X minus 1,500X squared. Next, we find the derivative of our revenue equation, which equals 2,625 minus 3,000x. We then set the derivative equation equal to 0 and solve for x. X is equal to 0.875. Therefore, the fare is 0.88 bir if we round up. This is the fare to be charged in order to maximize revenue in this case. That is all for today's lesson. We have solved some practical problems involving maximization and minimization. Until next lesson, thank you, teacher. Thank you, students.